Let's open the skeleton project. It has three files. The framework.h, which is a general header file. It contains a lot of utility structures and classes we have discussed during this semester. The framework.cpp is the entry point of the application. Both of these files belong to the framework, so I would recommend not to change them. Your playground is the skeleton.cpp, where your application should be implemented. Let's start with the framework.h. It includes several header files. stdio is needed because of the printf function, stdlib for the random function, math.h is for the trigonometric and logarithmic functions, vector is needed by the dynamic array, string is needed for the sophisticated C++ implementation of character strings. Windows.h should be included only if a Windows operating system is used, and the two really important libraries for us are the glue and the freeglot. Glue provides an interface to the OpenGL, no matter what kind of OpenGL version is implemented on our computer, and freeglot is the interface towards the operating system, and it's a portable interface. It allows our application to run both in a Microsoft Windows environment as well as in a Linux or even a Mac environment. These constants set up the default resolution of the application window. The first utility structure is the vec2. It is in fact the implementation of a two-dimensional point represented in Cartesian coordinates. For operator overloading, we implemented the basic operations, and the rule is the following: that we apply exactly the same operation for x and y coordinates independently. The global functions implement vector operations like the scalar product or dot product, the computation of the length of a two-dimensional vector, the normalization of a vector, which means that we return with a vector that has the same direction but its length is 1. And operator star allows the multiplication of the vector by a scalar where the scalar stands on the left-hand side. Vec3 is a three-dimensional point represented by three Cartesian coordinates, and it can also represent a color in RGB format. Again, we have implemented the possible elementary operators with the rule that all coordinates go through these operations in the same way and independently of the others. We can compute the dot or the scalar product for two three-dimensional vectors. We can compute the length, we can normalize the vector, and we can even compute the cross product of two three-dimensional vectors. Vec4 is also a three-dimensional vector expressed in homogeneous coordinates. So for a point in 3 dimensions we need 4 scalars. Alternatively, this vec4 can also represent a color in an RGBA, where A stands for opacity format. Again, we have the implementations of elementary operators. We can compute the dot product for two 4-element vectors, and with this we can even determine whether a point is on the plane or not, and if it's not on the plane we can determine whether it is on one side or on the other. So this vec4 can also represent planes defined by the 4 parameters like a, b, c, d. Mat4 is a 4 times 4 matrix. A 4 times 4 matrix has 4 rows. Each row consists of 4 elements. The 16 parameters of a 4 times 4 matrix can be constructed one by one, or we can construct with its 4 row vectors. In case of affine transformations, these 4 row vectors have intuitive meaning. The first vector describes what happens with basis vector I during this transformation. The second vector describes what happens with basis vector j. The third vector describes what happens with basis vector k, and the force vector defines where the origin goes when the transformation is applied. We have the index operator, so we can even use the double indexing to get one particular element of this 4x4 matrix. For the operations, we can multiply a 4-element vector and a 4x4 matrix. So if the 4-element vector is a point, this is in fact the execution of the transformation of the point with that matrix. We can multiply two matrices. This is just a concatenation, and the resulting matrix will be a transformation that executes both transformations one after the other. There are global functions that act as constructors. We can construct a 4x4 matrix that can do a translation. The input parameters, in fact, the translation vector. We know how to include it into a 4x4 matrix in order to establish a translation. Scale matrix prepares a matrix that can do scaling with a factor of s.x in the direction of x, s.y in the direction of y, and s.z in the direction of z. Rotation matrix is the implementation of the Rodriguez formula, so it can rotate around an arbitrary direction axis that goes through the origin, and the other parameter is the angle of rotation. We can have textures that are wallpapered on surfaces or two-dimensional regions. Basically, there are two constructors for the texture. The first constructor can use a file, and this file must be a BMP file, so it can load the image or the texture from a file. Or the texture can also be generated procedurally when we obtain a two-dimensional image that is typically computed by an algorithm. The create function of this texture class not only copies the texture to the GPU, but also initializes those hardware elements, the sampling unit in particular, that participates in the texturing process. Finally, the most important class is the GPU program that represents the vertex shader, the geometry shader, and the fragment shader running on the GPU. The geometry shader is not obligatory, but we have to specify a running and correct vertex shader and fragment shader. Initially, these parameters are 0, and during the construction, we store the identification numbers in these variables. The private functions of the GPU program are responsible for checking and printing the possible compilation or linking errors. GetLocation finds a uniform variable by name and returns its address or location. This address is needed because when we want to change the value of that uniform parameter, this address information is needed. In the constructor, we have a weight error input parameter that decides whether the program should stop when it encounters a compilation or linking error, or it can continue without stopping, just ignoring the error message. The create function creates these shaders based on their source code. The 3 source codes are character strings on this level. As I said, the geometric shader is optional, so we can skip the definition of the geometry shader. In addition to the vertex shader and the fragment shader, we should also specify the name of the output variable that is connected to the frame buffer. Well, this function starts with creating a vertex shader ID, then copies the source code into the OpenGL library, compiles it, and checks whether the compilation was successful. Then the same steps are repeated for the geometry shader and also for the fragment shader. So when all these shaders are available, we create the program. The shaders are added one by one. The output is identified, that output which is connected to the frame buffer, so that output which will specify the color of the pixel. the shaders are linked together. We also check whether there is a linking error, and finally we make this program active, which means that this program is going to run. Activation can be done later on with this use function. And the remaining member functions can modify uniform variables, and there are different versions based on the type of the uniform variable. There is a version which can set integer, a float, a vec2, a vec3, vec4, or even a 4x4 matrix uniform variable. We can even make a texture active in a uniform variable. And when it happens, the associated sampling unit is also initialized. The other part of the framework is the framework.cpp, which is just the entry point of the application. Here we can see the declarations of event handlers. These are only declarations, so the functions do not have any body. It will be our responsibility to define the behavior of these event handlers, so the bodies will be defined in the skeleton.cpp file, which is our playground. The main is here. It starts with initializing the GLUT framework. It sets the actual OpenGL version, so in this particular case we are going to use OpenGL 3.3. The window size is initialized, and also the window position is initialized. The initialization is a little bit different for Mac or Apple computers. Having defined the initial resolution and position of our application window, we can tell OpenGL or GLUT that a single pixel will store 8-bit RGBA information, and there will be 2 frame buffers in order to allow double buffering, and for each pixel the system will also store the distance of that particular surface whose color is written into the frame buffer. This information can be exploited in 3D hidden surface elimination algorithms. GLUT create window creates the window with a caption bar text that is similar to the program name. We use glue. This glue experimental is really a magic. It means that glue is able to figure it out what function can be supported by OpenGL, even if the driver does not explicitly state that. And then glue is initialized. I have to emphasize that this is the point from which we can issue any OpenGL call, because before this step, OpenGL is not initialized. It has really bad consequences if we try to call OpenGL functions without initialization. The program prints our current OpenGL version and the GPU type which we are using. Finally, the application-dependent functions are registered as event handlers. Main calls the onInit function, where the application can contribute to the initialization process. OnDisplay is registered for the event called display, which happens when one part of the application window becomes invalid. OnMouse is registered for the event when the user presses a button on the mouse. OnIdle is registered for the event, which means that time flies. OnKeyboard to the keyboard event when the user pressed the button, keyboard up when the user released the button, and motion when the user moved the mouse while one of the buttons are pressed. Finally, the system goes into the main loop that checks whether events happened to which we registered an event handler, and if this is the case, the event handler is automatically called. The playground, that is our application. The skeleton.cpp includes the framework, so we have the vec2, vec3, vec4, 4x4 element matrix, etc. readily available. This file starts with two simple shader programs. The first one is the vertex shader. So here, this is just a character string, which is nothing but the source code implementation of the vertex shader program. It's according to the OpenGL 3.3 version. For floats, we use high precision, which means 32-bit representation. This program has a single uniform variable, a 4x4 matrix, and it's called MVP. It will represent the model view projection transformation, which transforms objects to normalized device space. This program has a single varying input. It assumes that the input register 0 contains a two-element vector, and we will refer to this input register 0 with variable name VP. The implementation of the program is pretty straightforward. We take the input parameter, which is nothing but the x and y coordinates of a point. These two-dimensional Cartesian coordinates are extended to 3 dimensions, and Cartesian coordinates are converted to homogeneous coordinates by adding a 1. And this 4-element vector is multiplied by the 4x4 matrix, standing for the model view projection transformation. The result is in normalized device space, and vertex shaders should always output the point specifying its location in an output register called GL position. The fragment shader is also pretty simple. It's according to OpenGL 3.3. Floats are represented in 32-bit precision. It has a single uniform variable and a single output variable, which will be written to the frame buffer. And as far as the program is concerned, the output variable will be the input variable, which is a uniform variable, extended from RGB representation to RGBA. As a uniform variable is constant for all data elements, for all fragments in this case, we will have a constant color object. The GPU program will be created and initialized in the onInit function and will be used in the onDisplay, so we have to define it as a global variable. And additionally, the scene object is created in the onInit and will be used in the onDisplay as well, so its reference or identification number is also a global variable. So let's see the initialization. First, the photograph is placed on the output window. We specify the lower left corner and the width and the height of the viewport. Note that it means that the full application window is covered by the viewport. So the full application window will be the target of the rendering process. We are going to have a single object. Objects are identified by VAOs, vertex array objects, in OpenGL. First, we ask for a single VAO identification number and bind it, since all subsequent operations will refer to this particular VAO. A VAO may have one or more buffers or arrays called VBOs or vertex buffer objects. Here we ask for a single VBO and bind it as well, because these operations will refer to that VBO which is just created. This VBO will contain the location of the 3 vertices of our triangle. The 3 vertices are specified in the memory of the CPU. We have just a float array containing 6 float values, where each pair of these values is associated with a single point. The vertices array is copied to the GPU. We have to specify the starting address of the copy operation and should also tell OpenGL how many bytes should be copied. This GL static draw means that we want OpenGL to copy this array to a memory location, which is very efficient to read, but it may not be that fast when the data is modified. as we are not going to modify this array, this is an optimal solution. Then we should explain OpenGL how to interpret data stored in the VBO. So we will use input register 0 of the vertex shader. And when one vertex is processed, we have to copy 2 floats into the input register number 0 without any additional normalization, and we can assume that these data are tightly pegged. So whenever one vertex is over, the next vertex starts from that point without any extra gap. So with this, the array storing the triangle vertices and the VAO storing the array are created. We also create the fragment shader and the vertex shader programs based on their source code implementations. OnDisplay function was registered to the event indicating that application window has become invalid, so we have to redraw it. Whenever it has become invalid, the GLOT calls this onDisplay function and usually expects that this onDisplay function regenerates the content. So the implementation starts with the definition of the clear color, so it's black, and we clear the frame buffer memory for all pixels of the application window. Then first we ask the location of the color uniform variable. This GL getUniformLocation function returns its address, and using this address we can modify the value of the color uniform variable. So we set this value, recall that it's a vec3 variable, to 0, 1, 0, which is just a green color. Similarly, we ask for the location of the uniform variable called MVP and copy the content of this 4x4 matrix into that uniform variable. So we use the location of uniform variable MVP. We are going to copy just a single matrix right now. This is the starting address of the copy, and we tell OpenGL that the 16 floats stored in this 4x4 matrix should be interpreted according to the row major low, which means that first the rows are specified. This is the typical organization of two-dimensional arrays in C or C++. The uniform variables are set. Now we bind the single object, what we have, because the next function, GLDrawArrays, should draw that object which we have already specified. This is the point when we tell OpenGL that the vertices encoded in the buffer inside the VAO form triangles. We should process the VBOs from the very beginning, from index 0, and we should process 3 elements altogether. This is a very wise decision because we have only 3 elements in the VBOs. So this function will draw a single triangle. Because of double buffering, we call this GLOT_SWAP_BUFFERS function, which exchanges the rows of the 2 buffers. So we allow the user to see the result of rendering. These are the event handlers, so when the user presses the key, we usually do nothing except for the case when the pressed key is D. In this case, we invalidate the application window. As a result, GLOT will automatically send a display message, so our triangle will be redrawn. When the mouse is moved with a button pressed, we just print out the location of the cursor in normalized device space. Note that the input of this function is the pixel coordinates of the operating system. Operating systems usually have a coordinate system where the origin is in the left upper corner, while OpenGL uses a coordinate system where the origin is in the left bottom corner, so the Y coordinate should be flipped. I should also mention that this simple transformation is valid only if the viewport covers the full application window. So in case of mouse clicks, this program prints out the location in normalized device space. It also tells whether the button is pressed or released, and also whether it happened on the left, middle or right mouse buttons. On idle informs us that time flies, so this event is called in all cases. The reaction is pretty simple. We get the time elapsed since the starting of the program. We get it back in milliseconds, but we don't do anything with this result.